we have the powers of I here, and I to the first is just I to the second is -1, because it's the square root of -1 squared, right? So when you square a square root, you get just the radicand, right? -1. And then I cubed is -I, and I to the fourth, we're back to 1, so I to the fifth would equal I, because it's just I to the fourth times another I, right? So 1 times another I would just give you I. And then I to the sixth would be
-1.
-1. And I to the seventh would be
-I.
-I. And I to the eighth would be 1. And I to the ninth would be
I.
And I to the 10th is,
-1.
and I to the 11th is, and I to the 12th is 1. Alright? So, you hopefully now see a little bit of a pattern here. Okay? We have this cycle going through. Every fourth power of I, we're back to 1. Okay? What are some patterns that you see, other than every fourth one is 1? Lexi?
Every positive root, any even root is 1 or -1.
Okay, good. Every even power is either 1 or -1. Okay? So if you see I raised to any even power, you have a 50-50 chance of guessing it right. Okay? Even if you didn't even look at it any closer than that. Alright, hopefully you'll do better than that, but there you go. What other pattern do you see, Gloria?
Like every is 3, like 3, 9, and is 3, 6 is equal to -I. Like 11 and 3, like odd number.
The odd numbers are equal to
-I. Like
-I or
1.
no. The odds 1, 3, 5, 7, 9.
Oh, I.
Either I or -I. Okay? So here's the deal. If we have I to an odd power, we get an imaginary number, either I or -I. If we have I to an even power, that means we have a real number. Okay? Either 1 or -1. Okay? Now how would we figure out what it is exactly? Can someone give us some kind of a strategy here?
You divide it by 4, and then whatever the power by 4, and then whatever your remainder is, you just use the 4 possible I values.
Okay, good. You're dividing by 4, so, for example, if I wanted to find I to the, 75th power, I would take 75 and I would divide it by 4. And I would get 18 with a remainder of 3, okay? So what is it? It's -I, okay? Because that remainder tells us kind of the equivalent. It's I to the third power. So that is a -I. And notice, no matter what we started with, we'll get down to I to a first power at most. Okay? Now, you might say, well, what's with the 18? What does that stand for? Well, that means there are 18 sets of 4 that we could have kind of put together. In here, between the I to the 75th and this, okay, there are actually I to the 4th times I to the 4th times I to the 4th times I to the 4th 18 times. Okay? Well, all of those equal 1. Alright? So, that's why we can ignore the 18, just look at the remainder, and that'll tell us, what we need. So really, you just need to know these first four. You can figure out the rest. Okay? So that's a basic skill there with dealing with I. So let's look at the complex numbers a little more generally. The values with I are our imaginary numbers, so we have real numbers as well. When we put these together, we have our complex numbers. If you believe it or not, the complex numbers are the broadest category of numbers that we have. Okay? They're the broadest because if we were looking at this in terms of some sort of a Venn diagram, okay, you'll notice here the complex numbers incorporate A plus BI. It's a combination of real and imaginary. Okay? We have imaginary numbers. Okay? That's the stuff that just has a BI in it. Something with an I. And then we have all the real numbers. Okay? Those are just the things that have that part A in there. But when we add them together, we have the complex numbers. Okay? So you've been working with these since you could talk, right? You could count 1, 2, 3. You've been dealing with complex numbers because all the real numbers are part of the complex number system. Okay? So. Now, one thing I want to point out here is that in order for two complex numbers to be equal, then notice what this says is A plus BI has to equal C plus DI. In order for that to be true, A and C, the real number portions of those numbers, have to be equal. Okay? A has to equal C, and then also B and D, the coefficients of I on the imaginary portion, have to be equal. Okay? Now this is kind of a simple concept. I mean, in order for 3 plus 2I to equal another complex number, the other complex number has to be 3 plus 2I. Okay? That's simple in concept, but it's really easy to forget when we get to actually solving problems. Okay? So, now another thing I want to highlight today is, good idea. Another thing I want to highlight today is the fact that in our real number, when we're dealing with these complex numbers, we can treat the I just like we would a variable until we get to the very end. Okay? So, for example, if I were doing any of these operations, I would treat it just like I would treat an x. Okay? Here, if I were combining these, I have 11 minus a negative 3, that's 14. I have negative 2i minus 6i, that's a minus 8i. Can I put these together? No, they're not like terms. One's real, one's imaginary. Okay, so there's my solution. If I'm multiplying two complex numbers together, what do I have to do? I've got a FOIL. Okay? I've got a FOIL. I've got a 12 minus 18i minus 4i plus 6i squared. Okay? Now, here's where the difference is. When I'm going to my final answer, I've treated it like a variable up to this point, but what am I going to do here as I go to get my final answer?
You're going to subtract 4i from negative 18i and change 6i squared to negative 6.
There you go. That's the key. This is now a negative 6 because I can substitute in negative 1 for I squared.
Is your number can not add it for your
Sure. Okay, so we now have 12 minus the 22i. We do combine those like terms, but we also substitute in. And notice my final answer, 6 minus 22i, is just a complex number, and I is just to the first power. So here's the thing, when you're dealing with complex numbers and doing different operations with complex numbers, you should end up with complex numbers. Okay? We shouldn't have I squareds or this quadratic kind of form or anything. Okay? When I go to simplify this, can I combine these?
No.
Could you put together an x squared and an x cubed? No. So can we subtract when there's a I squared and an I cubed? We can simplify it though. Okay. So this 4i squared would be negative 4, and then we'd have minus 2 times what's I cubed? Negative I. So plus 2i, and there's our solution. So you can simplify, but the same rules that apply for dealing with an x squared and an x cubed apply here when we're dealing with a y squared and a y cubed. You can't just add them together. Okay? All right. One last one here. Another thing where we need to treat it just like we would a polynomial situation. If I have 1 minus 2i quantities squared, what am I going to have to do with that? I've got to FOIL it. We've got to write it twice. 1 minus 2i, 1 minus 2i, okay, and FOIL. And you guys know how to do that at that point, but same thing here. 1 plus 2i times 1 plus 2i. Okay, we FOIL them both. So 1 minus 4i plus 4i squared minus, the other thing here, make sure you distribute your negative. It would be 1 plus a 4i plus 4i squared. Okay, and then you can look to, as we distribute the negative, 1 minus 1 is 0. Negative 4i minus 4i is a negative 8i. And 4i squared minus 4i squared is 0. So that canceled that out. That canceled that out. We just have a negative 8i for our answer. Okay. So that's why I say until you get to the very end, you don't need to, substitute in or whatnot. You can treat it just like a variable. Okay? Any questions so far? All right, good, good. Now, the one thing that can be a tad tricky is when it comes to rationalizing denominators. Okay? Rationalizing denominators. Before we get to the more challenging one, if I had something like this, like a 3 over 5i, okay, how would you guys know that to rationalize a denominator, we're not allowed to leave any square roots or any radicals in the denominator, all right? Well, just because it's written as an I doesn't mean that it's something different, okay? This is a radical. So I need to get that I out of the denominator. And how would I go about doing that? Yvonne?
Times 5i over 5i.
Good. We can multiply it by 5i over 5i. Is there something else that we could do?
We can just times I.
Okay, good. We could just do the I over I, right? The 5 is already a real number. It's not a radical. okay? So it's allowed to stay in the denominator. I'm just going to multiply by whatever that radical part is. Otherwise, I'm going to have to reduce at the end, okay? So it's not wrong, it just adds an extra step. So if we then multiply, we have a 3i in the numerator, and what does the denominator end up being? A minus 5, okay? A minus 5. All right? All right. So that's nice for those kinds. What about ones where we have something like this, okay? Oh, by the way, standard form is just what we were talking about, the simplest radical form it's sometimes called, or you'll see it, or it's also described as just rationalized, the denominator is rationalized, okay? Anyways, it's all talking about the same thing. If we do this, 2 plus 3i over 4 minus 2i, and we tried to just do a times I over I like we did on the last one, we would have to distribute, okay? And all that would really do, in this case, it would be a 2i minus 3 once we substitute it in for I squared, and it would be a 4i plus 2. So we got rid of the I that was with the 2, but now we have one that's with the 4. So obviously we need a different strategy. We've got to do something different. Okay? Does anyone know what we should do?
We should do 4 plus 2i.
Okay. Gloria's saying we ought to use 4 plus 2i. Now can someone, now that you see that there, she's right. Can someone explain why we should use 4 plus 2i?
Because that gets rid of the denominator completely.
Okay, that'll get rid of the radical in the denominator completely. You know, what those are called?
The opposite?
Close. I mean, negative 2i and positive 2i are opposites, but when you have a binomials, the binomials are the same except for the sign in the middle. Do you remember what those are called? When you're factoring the difference of squares, it factors into these. What?
Converses.
Conjugates?
Conjugates.
Conjugates?
Conjugate numbers.
All right. These are conjugates, and these are actually, since we're in the complex number system, these are what are known as complex conjugates. All right. And the whole point of using these is when you're multiplying complex conjugates together, you end up with a real number. Okay. And that's because when we multiplied conjugates in the past, you remember the outers and the inners canceled out. Okay? If you look back at the example that we did, okay, back here, when we multiplied the outers and the inners together, that's where these came from, and that's where the imaginary part of our answer came from, right? So if we can get these to be opposites to cancel out, then we'll just have a real number in our solution, okay? So that's why we use the conjugate, because we have 16, it'll be a plus 8i minus 8i minus 4i squared, okay? And notice here, this is the whole point of doing this, the plus 8i and the minus 8i cancel out to 0. And now our denominator, I'll get to the numerator in a second, when I sub in a negative 1, it's 16 plus 4. So I get 20 in my denominator. Okay? Does everyone see how we did that? Okay? Now the numerator, it's okay that the numerator ends up with imaginary parts. Okay, we just have 8 plus 4i plus 12i plus 6i squared, and that simplifies into 2 plus 16i. Okay? Now, one other thing that I want to point out here is, and this is part of standard form as well. Okay, standard form has a little bit more to it than just saying simplest radical form or rationalized. The extra part it has is that they want that a plus bi look. Okay? So what I would need to do is I would need to separate this into a real part, 2 over 20, and then the imaginary part, 16 over 20, times the I. Okay? And then I could reduce both of those. So my final answer would be 1/10 plus 4/5 I. Okay? Take a look, let it sink in for a sec. Make sure you understand what's going on there. Alright, so we rationalize the denominator, we split it into the real and imaginary parts, we reduce each one, okay, to get our final answer in standard form. Okay?
So does it always have to be in standard form, or when there's like two things present? Like the last one, we didn't do that.
What do you mean, the last one?
The 3i.
Oh, this one technically is standard form because the real part is 0. And we could, I mean, you could rearrange the negative a little bit and make it minus 3/5 I, okay? I mean, you can rewrite it, but yeah, when there's only one term to it, that's just by nature standard form there. So, good question. Anything else? All right. Let's try a couple. We'll get through what we can. All right, we've got, what, 15 minutes? Yeah, we've got till 11:05. All right. So, I'm going to give you 10 minutes to work with somebody, okay? To try to work through these. If you're both stumped, if you both can't figure it out, okay, then you can ask for help, okay? But go ahead and try these, and then we'll take the last 5 minutes to go over them, okay? Feel free to work with somebody. If you're watching the video, you can skip the next 10 minutes, because I can't pause. So, yeah.
Mr. Negative. So you have to stop to the bottom. Right, got that. Then change it into this, which was what.
Yeah.
And then let's multiply the conjugate.
Yeah, now you did it the right thing.
Alright, so is the conjugate, would it conjugate opposite of number two? So would we conjugate 12i or just the second number?
No, it's just the second number opposite.
When I do this, positive 100. Let's see. So this becomes 2 6s.
Okay, but the I squared makes it negative.
Oh, so it becomes negative 6
Negative 1.
plus negative 6 plus 9. Very good. 4.
Yeah, go ahead and practice putting them in standard form.
That multiplied by itself, and you get like negative 144 minus 24, which is Why would it be negative 25 by not positive?
Because this was a positive, and you're multiplying it by a negative 5. Now, let me point out one thing here with the first one that most of you that I saw were done with it. Okay? If you turn this around and made it 5i over 12i minus 5, did you do that? And then you use the conjugate 12i plus 5 to multiply?
Yeah.
If you did that, you'll get all the same stuff eventually. What you may have gotten, though, would have been, at the end, you would have gotten a negative 60 plus 25i over a negative 169. This is where standard form is helpful, because both of those are equivalent. But when you split it into standard form, okay, you would make the negative over negative for 60 over 169, which would give you a positive 60 over 169. Okay? And then you'd have a positive over a negative for the 25i over negative 169, which would give you the same thing that we have over here, minus 25 over 169i. Okay? Does that make sense?
Yeah.
That's why standard form is kind of nice because no matter what path you take to get there, if you simplify stuff, we'll all get the same answer. Okay. What do we have to do with this one? 2i over 2 plus I plus 5 over 2 minus I?
If you do two separate, like the 5 over 2 minus I, you'd have to multiply that by 2 plus I over 2 plus I. And then you have to multiply the other one by 2 minus I over 2 minus I.
There we go, 2 minus I over 2 minus I. And whether you're thinking about getting a common denominator or using conjugates, in this case you would do the same thing. Okay? Getting a common denominator, you'd multiply the two denominators together anyways. Alright, but what we have here then is 4i minus 2i squared. Since they're going to have a common denominator, I'll just put them all over the same thing. And then that's going to be a 10 plus 5i. And this whole thing will be over 2 plus I times 2 minus I, which comes out to what? 5. Yeah, 4 minus I squared, which is 5. Okay? So that's over 5. The numerator simplifies down to what?
I plus 12.
Okay, we've got a 9i, and negative 2i squared is a positive 2, right? Plus 10 is 12, so 12 plus 9i over 5. So in standard form, that would be 12 fifths plus 9 fifths I. Okay? Any questions so far on these two? All right. How about our last one? How did you start the last one? Right?
I in the numerator? Or I've heard of that.
Like make it 9i over 5? Yeah, that's okay. When you look in in the book or something, you'll see it written this way, so I'm just getting you used to seeing it. But yeah, you can put 9i over 5. Okay, how would we start this one? Gloria?
We can put them together like 4 minus I times I, and then for the top is like 1 half I times 4 minus I.
Good, good.
And then for like minus 3I.
Okay, good. We'd multiply this one by I over I. So we're getting a common denominator here. Is it going to rationalize them? No, but we can deal with that later. Okay? You have the option here. You could either rationalize both denominators first and then get a common denominator, or like Gloria did here, we're getting a common denominator first and then rationalizing it at the end. Either way will work. Okay? So if we did this, we have 4 plus 4i minus I, so plus 3i minus I squared. It's going to be over a common denominator, so I'll put it all over there. It's minus 3i. Guess I didn't need all that. Okay? And then our denominator is 4i minus I squared. Okay? So this whole thing is going to then be 4i plus 1 in the denominator. And in our numerator, we actually just have what? What's our numerator equal?
5. Wait. 4, 3, 2, 5.
Hey, you're right. It's just
5.
5. It's just 5. 4 minus a negative 1 is 5. And the 3i and the minus 3i cancel each other out. Okay? Everyone see that?
Yeah.
Okay? So now we have to rationalize, so what are we going to multiply by? Good, 4i minus 1. Okay, so we then have, and I'll get it in the right order here, I'll put the real number part first, negative 5 plus 20i over, what is this going to give us? 16i squared minus 1. Negative 17, right? Negative 17. So now, in standard form, it's going to be a positive 5/17 minus 20/17 I. Okay? To get the what? This? I got the common denominator, so I times 4 minus I. And then I did this times this for these parts.
But not now.
And then just a minus 3i for that. Since I knew I had a common denominator, I just put them together. Alright, see you guys. Have a great day.